test for two-sample difference of means. So we're going to use our diamond example. I can't remember if we did this one with confidence intervals or not, but we're going to do it now for hypothesis testing. So weights of diamonds are measured in carats. 1 carat is 100 points, 0.99 carats is 99 points, etc. The difference between a 0.99 carat diamond and a 1 carat diamond is undetectable to the naked human eye, but we want to find out, does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? So we're going to see if there's a difference between the average prices. And we want to be able to compare the equivalent units. So we're dividing the prices of the 0.99 carat diamonds by 99 and the 1 carat diamonds by 100. So we're getting the price per point. So we want to see if there's a markup for a 1 carat diamond. If it's more expensive per point. So we're comparing the average point prices. Here's the data. This is a random sample from a data set in this R package. So we took a random sample of 23 99 point diamonds and 31 carat diamonds and found their average point prices. We got an X bar of 44.5 versus 53.43, and these are our standard errors. Our N is not at least 30 here, but based on the box plot, the data do not look extremely skewed. So, no outliers, so we should be good there. So, our parameter of interest is the average difference between the point prices of all 0.99 carat and 1 carat diamonds. Our point estimate is the average distance between the point prices of the sampled 0.99 carat and 1 carat diamonds. Which of the following is the correct set of hypotheses for testing if the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? It's C. We are specifically looking for higher than average, not difference. So this is a one-tailed test. So A would be the two-tailed test. B would be seeing if the 1 carat diamonds were less expensive. D has X bar instead of mu. Which of the following does not need to be satisfied in order to conduct this hypothesis test using theoretical methods? We do not need to have both sample sizes at least 30 if the distributions are not extremely skewed, right? The prices should be independent within samples and independent between samples, and we should check for skew and outliers, but if we do that, they do not need to be at least 30. Again, we are doing a t-test for the difference of two small sample means. That's the, again, point estimate minus the null value over the standard error, where the standard error is S1 squared over N1 plus S2 squared over N2, and you take the square root of that whole thing. So the degree of freedom is the smaller of the n's minus 1. There's a complicated way of finding the degrees of freedom on a calculator, but this works for our purposes. So our t is going to be our point estimate minus our null value over the standard error. That would be our general formula. Our specific formula, it's going to be the x bar of the 0.99 minus the x bar of the 1 minus the null. Our null value is 0 over the standard error. This is s of 0.99 squared over n 0.99 plus s of 1 squared over n of 1. And so we plug in for our x bars and our s's and our n's, and we put it all into the calculator, and we get a t-score of negative 2.508. So you can do this on the table, but you're probably going to do it in your calculator. So this was a one-tailed test, so we don't multiply by 2. It's just TCDF of negative 199, negative 2.508, 22 degrees of freedom, and it's 0.01. It's ever so slightly more than 0.01, but it's basically 0.01. So if you do your p-values using a table, you don't get an exact value, you get a range of values, which is why the answer choices are that. But we're going to use the calculator, and that gives us an exact value, right? And so we're looking for the lower tail of this distribution. That's what your sketch is going to look like. What is the conclusion of the hypothesis test? And how would this change your behavior if you went diamond shopping? Right? Our p-value is small, so we reject the null. Right? 0.01 is less than our alpha of 0.05, so we reject the null. The data do provide convincing evidence to suggest that the point price of 0.99 carat diamonds is lower than the point price of 1 carat diamonds. So if you went diamond shopping, maybe buy a 0.99 carat diamond. It looks just like a 1 carat diamond, but is significantly cheaper. Or, buy lab created fake diamonds. They're still shiny and they're like $200. What is the equivalent confidence level for a one-sided hypothesis test at alpha equals 0.05? So if your alpha is 0.05, a confidence interval would also have 0.05 in the other tail. It's going to be 90%. So if it's a one-sided hypothesis test at an alpha of 0.05, your equivalent confidence interval will be 90%, not 95%. So your conditions for inference, for difference of means, random, normality, and independence. Simple random sample. Check both populations for normality. Either your population is normal and your n can be any size, or your population distribution is unknown and your n is at least 30, or your population is unknown, your n is less than 30, your sample has no strong skew or outliers. And then check the 10% and that the samples are independent of each other, or that it is at least reasonable to assume that they are. Standard error for the difference of means, square root of the sum of the variances of the two sampling distributions. We know how to do this. For a one sample t interval, we use n-1 for our degrees of freedom. For a two sample t interval, there's a very complicated formula, but we're going to use the smaller of the n's minus 1. Researchers at Yale carried out an experiment where they sent out resumes to faculty at academic institutions for a lab manager position. The resumes were identical, except that on half of them the applicant's name was John, and on the other half the applicant's name was Jennifer. Unlike in the match pair scenario, each faculty member received only one resume. We're interested in comparing the mean salary offered to John relative to the mean salary offered to Jennifer. Instead of taking the average of a set of paired differences, we find the average of each group separately and take their difference. Conduct a hypothesis test to see if the average salary offered to Jennifer is the same as the average salary offered to John. Use a significance level of 0.05. So, 4-part hypothesis test. We're going to state the parameter, which is the difference difference in average salary offered to John and Jennifer by all universities. Our statistic, our x bar 1, let's call x bar John minus x bar Jen, is going to be 30,238 minus 26,508, which is 3,730. Our null hypothesis is going to be that x bar John equals x bar Jen. Or you could say that x bar John minus x bar Jen equals 0. That also works. And then our alternative hypothesis, the question just says see if the average salary is the same. We're looking for a difference, but it doesn't say which direction. So it's going to be a two-tailed test. X bar John does not equal x bar Jen. Or x bar John minus x bar Jen does not equal 0. And our alpha equals 0.05. Our plan, this is a 2-sample t-test for mu John minus mu Jen. We check our conditions. We're going to assume that it's random. 10%, right? 127 universities is less than 10% of all universities. And technically it's an experiment. We don't really have to check 10% for an experiment. And the large counts, N1 is 63, which is at least 30, and N2 is 64, which is at least 30. Our general formula is that the test statistic is the statistic minus the null value over the standard error. For this, that's going to be a t is x bar John minus x bar Jen minus 0 is our null over the square root of s John squared over n John plus s Jen squared over n Jen. And we plug all of our numbers in, and that is 3,730 over the square root of 5,567 squared over 63 plus 7,247 squared over 64. Put all that in our calculator, and that's a t of 3.26. Our p-value is going to be, again, two-tailed test. It's a not equal, so two-tailed test, 2 times the TCDF with a lower bound of 3.26, an upper bound of 1E99, and a degrees of freedom, the smaller of our n's minus 1. So degrees of freedom is 62. And our p-value here, kind of hard to see it now because I wrote all over it, but our p-value is 0.001. So then our conclusion, because our p-value 0.001 is less than our alpha of 0.05, we reject the null. We do have convincing evidence that the salary offered to John is different than the average salary offered to John is different than the average salary offered to Jennifer for all universities. And this is another one that we did confidence interval for. An instructor decided to run 2 slight variations of the same exam. Prior to passing out the exams, she shuffled the exams together to ensure each student received a random version. Anticipating complaints from students who took version B, she would like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult on average than version A. So we are specifically testing if it is more difficult, so that is going to be a one-tailed test. And we are going to conduct a hypothesis test to see if the 2 exams, the scores on the 2 exams are the same. But we're going to do this as a one-tailed test because we specifically want to see if version B is more difficult. So, our 4-step process, we state the parameter, which is the difference in average scores on version A and version B of the exam. Our statistic is going to be X bar A minus X bar B. X bar A was 79.4, X bar B was 74.1, which is a difference of 5.3. Our hypothesis, our null, is that there is no difference, which is X bar A minus X bar B equals 0. Our alternative is that version B was harder, that the average score on version A, or the average score on version B was lower than on version A, which means that the difference would be positive. Right, we're testing if the difference is positive is our alternative if we're doing this as a one-tailed test. So, and then our alpha equals 0.05. This is a 2-sample t-test for mu A minus mu B. Our conditions, random, they were randomly assigned. Yeah, or random version, I think is what it says. Random version. The 10% condition, it's an experiment. We didn't know sampling, so the 10%, so no sampling. So we don't need to check 10%. And then both of our n's, NA is 30, which is at least 30, and NB is also 30, which is also at least 30. So that checks our normality condition. Our general formula, our test statistic is our statistic minus our null value over our standard error. For this, that's going to be that t is equal to X bar A minus X bar B, the null value being 0, over the standard error, which is the square root of SA squared over NA plus SB squared over in B, which is 5.3 over the square root of 14 squared over 30 plus 20 squared over 30, which is 1.189. That's our test statistic. If we sketch our picture, if the difference really is 0, the probability of getting a difference of at least 5.3 is going to be this way. Our p-value is, use the TCDF of 1.189, 1E99, 29 degrees of freedom. Degrees of freedom is the smaller of our n's minus 1, and that should give you a p-value of 0.122. Right, p-value of 0.122. So what is our conclusion? I'll write the conclusion up here. All right, interpret the p-value if our null is true, which is to say that mu a, that's a mistake that I made. My hypotheses should have mu, not x bar. Whoops. Hypothesis mu a minus mu b should be my hypotheses, not x bar. My bad. If our null is true, which is to say that mu a minus mu b equals 0, there is a 0.122 probability of getting an x bar a minus x bar b of 5.3 or higher purely by chance. And then interpret or make our decision, right? So since 0.122 is greater than our alpha of 0.05, we do not reject the null, and we do not have convincing evidence that version B is harder than version A. Ta-da! Hypothesis test done. Real quick, your reference for your standard error calculations. Again, for a 1 sample, your mean is s over the square root of n, and your proportion is the square root of p1 minus p over n. For 2 samples, your mean is the square root of s1 squared over n1 plus s2 squared over n2. And for a proportion, it's the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. If you're doing a hypothesis test, your p is p0 that comes from the null hypothesis. If you're constructing a confidence interval, you use p hat. If it's a 2-sampled, so use p0 for a hypothesis test for 1 proportion. If it's a 2-sample, you use p pool.